Here we discuss what we mean by one of the great conservation laws in physics, the principle of conservation of momentum, as it is embodied in the equations we've derived. So, Newton's second law for a system is indicating that for so long as the net external force on the system is zero, the time derivative of the momentum of the system would be zero, and therefore the momentum of the system would be constant. Also telling us that the velocity of the center of mass would be constant throughout any time interval during which this is true. Since this is a vector equation, it's telling us that the x component of the momentum of the system would be constant, and separately the y component of the momentum of the system would be constant throughout any time interval during which the net external force vanishes. That's one way to represent our conservation law. If we rearrange this equation into its integral form, into sort of the impulse momentum theorem form, we could talk about conservation of momentum in a slightly different way. Here we have the suggestion that if this integral, representing the impulse imparted by the net external force on our system, if this integral vanishes from time 1 to time 2, then the momentum of the system, the change in momentum of the system during that time interval is zero. Or more explicitly, the momentum of the system at the end of that time interval, that's T1, the momentum of the system at the beginning of that time interval is equal to the momentum of the system at the end of the time interval. Its starting and ending values would be equal if this integral vanishes. So we would say that momentum had been conserved during this interval. It ended up at the same value at which it started. Now, under what circumstances does this integral vanish? I can think of at least three possibilities. Most obviously, if the net external force on the system is zero the whole time, so if this is zero from time 1 to time 2, then our integrand being zero, the integral, of course, is zero. So if there's no external force, then the momentum of the system does not change. We described that above. The momentum of the system would be constant throughout that interval. But what about this? What if we have a net external force that was non-zero, but that was like varying in a very particular way, such that if the graph of the net external force, say in the x direction versus time, looks like this, where it was exerting a positive force for a bit and then a negative force for a bit, so it flipped directions, and the areas under the curves here, representing the impulses exerted on the system by that net external force, were equal and opposite, so they canceled out, suggesting that the net external force added some momentum in the x direction to the system and then removed an equal amount of x momentum from the system, so that at time 2, the momentum that was added had been removed and you were back to the total momentum that you had at time 1. So in this case, the integral here would vanish since the positive and negative contributions cancel, and the momentum at the end of the time interval would be the same as the momentum at the beginning. So we would say in one sense that momentum was conserved, but we would also have to acknowledge that the momentum of the system did change during that time interval. It increased for a bit, and then it decreased for a bit, and happened to end up back at the same value from which it started. So maybe a stricter use of the term conservation would require us to say that momentum wasn't conserved here. It changed during that time. It happened to end up at the same value as it started with, but it did change during that time interval. So maybe you consider that to be conserved, maybe you don't. But it is a way in which this integral could vanish over some time interval. Okay, the third possibility is the most subtle one. So I'm going to discuss another way in which that time interval could vanish. Another way in which that integral could vanish. If that time interval was very short, and if the magnitude of the net external force was limited to be finite, then we can imagine some graphs that looked like this. Say for a typical collision, let's imagine a collision here between two objects. We would have a brief external force that increased to a maximum and then decreased, and so that would be our duration of this collision here, and the area under that curve would represent our impulse. So that area would represent the change in momentum. But if the interval was very short, if the collision was brief, if delta t shrank here, if it shrank down to 0, if delta t shrank to 0, then that area shrinks as well. So if the force is limited to be finite, if the force can't get any bigger, if the max force is capped here, if the max force is capped and delta t shrinks to 0, so we have a very short interaction, then that area under the curve shrinks to 0. Our impulse is shrinking to 0, and the change in the momentum of the system would be shrinking to 0. And so our integral here would be vanishing if that time interval was very short. In other words, the net external force was not given enough time to alter the momentum of a system. A force has to act over time to impart an impulse. Here's an example of a case in which this could arise. Suppose we had 2 blocks on a surface, and B was sliding towards A with some initial velocity, and then they collide. And during the fraction of a second that they are colliding, that A is pushing on B, we would have these 2 equal and opposite contact forces between them. Force on A due to B, force on B due to A, and by Newton's third law, we would know that those are equal and opposite, but they would be internal forces. If the 2 blocks are inside our system, then these are internal forces, and they do not affect the momentum of our system. We know only external forces do. But suppose there was an external force present here in the x direction, namely friction, static friction between block A and the surface. That would be considered an external force if the surface was not inside our system. And so friction acting as an external force here could potentially change the momentum of our system during that collision. But if the collision is very brief, if the blocks are only hitting each other for a fraction of a second, friction would impart almost 0 impulse. The graph for the force of friction versus time would look like this. Our friction we know has a max value, it's capped, and if delta t shrank to 0, if the collision was very brief, then the momentum of the system just before the collision would be equal to the momentum of the system after the collision. We would say momentum was conserved in this collision because it happened so fast that friction, this external force, didn't have enough time to change the momentum of the system. On the other hand, suppose the blocks stuck together and then slid off to the right afterwards. Then friction acting over time as the blocks slid off to the right, so if they collided here and are sliding off to the right, slowing down due to kinetic friction now this kinetic friction is able to act over time because time definitely passes as the blocks slide. So here if we graphed friction versus time, starting from this moment here, once the collision was over, they'd stuck together at this time and were now sliding off together. Now that constant force of static friction would be imparting an impulse, the impulse that would be removing the momentum in the x direction and slowing the blocks down. So again, an external force does need to act over time in order to impart an impulse. And if your interaction is very brief, there might not be enough time. And so this integral could vanish over a short interval, allowing the momentum to be conserved from the beginning to the end of that very short interaction. Okay, one more note, sort of a second example on this question of very short interactions. Suppose we have some hypothetical immovable object. Well, this is not that hard to imagine. Say a block hits a wall. We know our wall is not going to move when the block hits it, so this wall we'd be treating as an immovable object here. So how do we model an immovable object? We can allow the wall to exert infinitely big contact forces during an infinitesimally brief time interval. That would be required in order to prevent the wall from moving. So to have something that truly cannot move, it needs to be able to exert infinitely big contact forces. So when the block hits the wall here and say bounces off, collide, bounce, during the fraction of a second the ball is in contact with the wall before it rebounds and heads off to the right, the contact force exerted on the block by the wall, graphed versus time, would look like this. The block is approaching the wall. Here, the block first contacts the wall. The wall exerts a huge force on the block for a very short time, a fraction of a second here, a millionth of a second, and then the block loses contact and continues off. So we could have a very short time interval here. Delta t could go to 0 during that collision. And that might make us think that this integral could vanish if our delta t shrunk to 0, like we were looking at here. But the difference between example 1 with friction and example 2 with the wall is that in example 1, friction was capped at a maximum value, limited to be finite here. So as delta t shrunk to 0, the area under the curve shrank to 0. With the wall, on the other hand, our hypothetical immovable object, it could potentially exert infinitely big contact forces, a contact force that is not capped. So as delta t shrinks to 0, in order to prevent that wall from moving, from budging even a millimeter, this force could jump all the way up to infinity. And strangely enough, it's possible for that to occur in such a way that this infinitely tall but infinitely thin rectangle here could have a finite non-zero area, indicating that the impulse imparted to the block by the wall could be non-zero. The wall could change the block's momentum during that very brief interval. And we know, in reality, of course it could. Like, the block has momentum in the negative x direction, then afterwards momentum in the positive x direction. So of course its momentum did change. Here, the area under that tall, thin rectangle, that is the impulse imparted to the block, changing the block's momentum. And I'm saying that in this case, the momentum of the block would not be conserved, even though the collision is infinitesimally brief. So in this case, this integral does not vanish. Even though delta t is very short, our integrand here gets very big, so this does not vanish, and our momentum is not conserved. To recap, we can express conservation of momentum in this derivative form or in this integral form, and we can think of at least 3 ways in which this integral vanishes. If it does vanish, then the momentum of the system at the end of that time interval is the same as the momentum of the system at the beginning of that time interval. And we went through at least 3 ways that we could imagine that happening.